Good morning, everyone. My apologies for a few minutes delay on this. Thank you so much, Debbie, for that wonderful invitation. So we're going to share almost a couple of years of research on air traffic pollution. The topic is conducted in autonomous systems, incorporating an air pollution into this particular system, for handling traffic congestion. My name is Krishnakumar Nedunuri, and we're going to do this presentation together with my colleague, Dr. Ramanitharan Kandiah. We are both from Central State University, International Center for Water Resources Management. This particular effort has been carried by our environmental engineering program. So very quickly, to get to the topic, I want to give viewers a background on the problem itself. You can clearly see the economic impacts, from air pollution and greenhouse gases. The economic downturn is going to be tremendous, and we're looking at over $100 billion impact in the next 10 years. It's just not the economics. You're also looking at the scale of environmental and health impacts due to increasing population and the associated congestion. So is it a good news? We have the safe, affordable, and fuel-efficient, vehicle rule, and in the years to come, in the next 5 years. So the goal is to reduce the emissions. The original goal is 5%, but it was reduced to 1.5%, and that just tells all of us, we're going to face an increase in consumption, and that would lead to additional carbon emissions, and that environmental cost is estimated $1.5 billion. The good news is, the US is now trying to get up on climate change impacts. And then we are all aware of a $2 trillion, proposal from President Biden. And then if you take a closer look at it, the transportation is getting, a lot of attention here, 620 billions. And then if you further go down and look at the different, elements of the transportation proposal, you can clearly see how important it is to, tackle congestion. And of course, the climate change forces to look at greenhouse gases, and all this leading to air quality. So there's a lot of impetus on air quality in the next years to come. So that being said, these emission models that we're going to use, we want to take readers on a path as to, in the past, what happened to these models. So typical emission models are trying to assess the traffic pollution from looking at the driving patterns and also the traffic densities, and then trying to get some sort of correlation between driving patterns and the traffic density, and then get some sense as to the pollution severity. So that kind of approach, unfortunately, is not accurate. We need to take local conditions into consideration, and traffic density, and also the nature of these emissions. Just basing the emissions on driving patterns wouldn't be accurate. But the advantage is, if we adopt the connected and autonomous vehicle approach to handling traffic, you can certainly understand that even if 5% of the traditional traffic is converted into CAV systems, that would reduce the traffic congestion. And of course, once the traffic congestion is reduced, the emissions are also going down, as you can clearly see. So there are certain advantages to using these autonomous systems, and the idea is as we reap benefits from those systems, we want to also monitor congestion and traffic pollution in these areas. So anything happened so far in this particular area? There are some recent studies which actually used MOVES is a mobile vehicle emissions simulator. It essentially calculates emissions from vehicles. So there are some earlier efforts on using that model in the CAVs. So that brings us to the our research goal. The idea is to alert approaching passengers into these congested areas ahead of time, how the air quality is going to look, and on a nice app. And with the CAV, you can imagine a fleet of vehicles carrying this app and then telling each other as to how the approaching conditions are going to be. So this is very, very advantageous and the best use of CAV systems in terms of understanding the air pollution, and as we pass through those areas, what kind of severity exists depending on the meteorological conditions. So that is the goal of an app, to alert the passengers to safety in case there is excessive congestion and associated pollution. Ramani, over to you.
Okay, so in this way, what we are trying to do is actually we are putting the project into 3 sections. The first thing is that finding out the emissions of the vehicles at a particular time, and then we will look into that, how that is actually dispersed near ground, or near ground, how this emission dispersed. Then finally, we are trying to make an app for that. So at this part, for the last 2 years, what we have done is that we have actually worked a lot in the previous 2 years on finding out a methodology to simplify the current existing MOVES simulator that actually gives you an accurate prediction, but at the same time, it is going to take more time to do that prediction. So that's our first aim, is to get a simplified version of the MOVES. In other words, a simplified version means rather than having every time we are producing it, we try to come up with a particular flat sheet data that can be substituted to calculate the emissions from a vehicle. So that's the first step. And the second step, what we try to do is we are taking the meteorological inputs around that area to do a dispersion model. So that when the emission happens from the vehicle, then it started to disperse on that area. So we have to do a dispersion model to do that. So the dispersion models also, if you look into that, there are a number of good models we see it, because C-line and R-line, I think Dr. Kumar will talk about that a little later. But only the issue with that is that then again, it will take more time to calculate. But if we are going to have an app to tell reaching passenger to a junction, we have to tell ahead of time, this is the situation over there, this is the concentration of the particular the gases around that area. So the passenger may have a choice to take another path to go the alternative path, or he or she will move towards this one. So that's the whole idea we do it. So as I said, we are doing this in 3 steps. And then, Dr. Kumar, next slide, please. So this is actually the methodology. We put it into in a screen. So what we do it here is, in this case, is that if you look into that, we actually get the current traffic. Usually we try to get the current traffic information from the traffic system monitors around that area. But if we do not have in time, sometimes it may not work just for different reasons. So in that case, we try to do the average, annual average data with a kind of correction for that particular month or particular time. And then we take the data. At the same time, we will try to get this MOVES model simplified version of pre-calculated emission from that area. Then we calculate the emissions coming from the vehicle for different gases. So we are going to talk about the gas a little later. Then we will use that data to get the dispersion model. And then we will compare that with the NAQUAS and greenhouse gas, the EPA allowable limit, then we will make the decision. So if you look at this schematic, some of the component that we show at the end, it's actually we are visualizing for a long time period. So that's what it is. So this is actually, this most of you already know it. This is actually our traffic data, where we get it. We get mostly the real-time traffic data to come estimation. It comes from traffic information management system. We get it. And then if you do not have that in that case, we use the annual average daily traffic data, but we do a little correction for that. And in addition to that, at this point, most of the data available, traffic data available, either it is the passenger cars or heavy trucks thing, so that our calculation also based on that one. That we haven't gone further because we do not have enough data to do. And then if you are using the AADT, in that case, we will do some corrections for monthly, hourly, peak hours, and other things to predict that. But as I said, we are using this motor vehicle is emission simulator to get the emission for different type of vehicles. Until March, they have the EPA as the model moves 2014. That's what we have calculated in the previous time. But now the moves 3, that actually revamped version, it has come. So what we are doing actually with our students, try to calculate this emission from different part of Ohio with a new one. So that's, again, we are redoing the thing because we wanted to be updated to the latest thing forward. Yeah, Dr. Kumar, US next.
So as you can see, our approach is to reduce the time. So what we do is, we strategically, run the moves, periodically and update the information on the emissions, get real-time data, traffic data. In Ohio, we have, TIMS, Transport Information Management Systems, from where we can get updated data. So given these two instruments, we are now in a position to calculate, the emission rate. And then, that feeds into a dispersion model, which would enable us to predict the concentrations, ambient air concentrations near road. So that is the goal, to be able to get near road, values, and then see, and from there assess air quality. When you look into incorporating the dispersion model, they can range from highly complex Gaussian models to more simpler analytical models, which take into consideration several parameters. We can actually boil down those complex models into simpler forms. For our purpose, where our main focus is on tracking emissions from line source, the line being the interstate and the vehicles moving along the interstate. So as you see, people have worked on this. We have quoted some references here. There are public domain models already in place. I refer to R line and C line models here. So there are these models that are available to us, but most importantly, these models are going to take a lot of time. So the idea is to come up with a dispersion model, that can quickly take conditions, real-time conditions, and then be able to predict reasonable concentrations. Ramani?
So when we try to have this selecting these models, we look few things in our in consideration. First is we try to come up with a model less complex, so that will be helpful for understanding and having less data to be taken and even may run quicker. Then is parsimonious. That's a kind of very simplified way of using the model. And the data, we want that when we have it, accessible data, easily accessible data, we want to be incorporated in this model rather than we have a very hypothetical, very brilliant model, but if we do not get the data that we want, then we will be in trouble. So we wanted to have a model with accessible data, then easy to understandable. Anyone who use this one, we want to see that to be understandable for that. So layman or whoever is using that. And it's a reliable data. When we get the data or if the model we run, that should be reliable. And finally, quickly computable. That is the most important one we wanted, because if we are going to use that for our app purpose and other thing, we don't want that to run for hours time when we need the things to be decided within a few minutes.
So having the necessity to make sure that the app has all these characteristics, which Ramani has just mentioned, as a start, to get some very quick estimates, we can do, a simple dispersion model on the left-hand side, I have that equation, where the concentrations are estimated, depending on how much emission is taking place from each of the vehicles right now or currently at the intersection. So, and that particular information, we can get it from moves. And then we can get real-time conditions on temperature, wind speed, and atmospheric stability. And with that particular information, we can quickly calculate concentrations. But we need to understand on the right-hand side, you can see, how the conditions are. You can clearly see the angle between the observer, or in this case, a station, and the moving traffic is important. In this, we are assuming, a perpendicular, orientation. It also matters, which way the wind is blowing. Wind direction is important. So those additional parameters, are important, and then can be easily, added, this to SDM, depending on the need. So the whole idea is to be able to use a simple model at the same time, calibrate with more established models, but which would take more time, and continuously, update our model, depending on, different intersections, based on their unique characteristics. Ramani?
So when it comes over here, the case, actually, we are doing all the case studies on the models and everything within Ohio, because we are convenient, because we have been doing traffic-related air pollution studies here almost at least 12 years. So that's what we are convenient with that. But whatever we do it with this data can be expanded to anywhere. So at this point, if I want to give a kind of introduction to Ohio traffic, if you look into that, it is almost 31,000 segments of the road. And then what are the things we are looking at this point is greenhouse gases when it comes, CO2, N2O, and methane. We look into that, how the emissions. And then the NRCS particulate matters 2.5 and 10 micrometers, and NOx and SO2 and carbon monoxide. These are the gas emissions, and the concentration near a road is what we are looking at this point. And as I have explained earlier, we are trying to look into the road, restricted road and unrestricted road, and two types of vehicle. That's the basic way we are trying to develop our model and the app. This is actually a kind of picture that gives the emissions from the vehicle. It's not a concentration. The emissions from the vehicle per day around Ohio highway network. And it's very clear if you look into that, 75, 71, and 70 and 95 are the places really high concentration emissions. And even you see, look into the cities, that is actually Cincinnati, basically it's Camden and Warren and Butler County, and Columbus if you come, Franklin County, Cuyahoga County, and Summit County, actually Cleveland and Akron. And then you will look into that. These are the highest emission places. And then after that comes Dayton, actually Montgomery County, and then Toledo, Lucas County, and probably Youngstown. So that is the idea on this slide. Next one. So when we look into that, we look more closely at 4 intersections. The first one is I-75, I-70, actually in Dayton, in Montgomery County. That's most of the slides that's going to follow here. It's actually, we have seen the results for that place. And the other thing that we have finished, but not we have shown all the results in this presentation, is I-71 and I-75 Cincinnati. That intersection has been identified as the 8th worst bottleneck of the country by the 2020 top track bottleneck list. That is the one, next one we are doing it. This is basically Cincinnati to on the other side to Kentucky, we go that around that area, what we have it. And then the other 2 that we are going to work on, that is the I-70 and I-70 in Columbus. That's a 97 thing, and then intersection I-90 and 71 Cleveland. So that's we are going to work on. Next one. So this is actually a typical Ohio, this one, transportation data management system. To traffic data, we got it. So this is the I-70-75 Montgomery intersection that we look. So here's the data. What are the data? From here, we are going to pull the data and we do the calculations. Actually, the one that we are going to see below is basically coming from that. Yeah, next. Yeah, so this is, if you look into that, when I talked about this intersection, I-70 and 75, and if you look at the bottom, this is a typical ADT values, and it also shows how much is the passenger and commercial vehicle. That's basically, we look into that in a way to look into how many cars, and what kind of thing, if you need that to use the ADT for our thing. Yeah, next slide. So this is actually gives basically the C-line model, the dispersion model that he has used, Dr. Kumar has used, and to calculate the concentration near near road concentrations around that I-75, I-70 location. And so this is actually, if you look into that, this is actually EPA model, the standard one, but it takes a little time to calculate it. So our whole aim is we are going to simplify this one to move to the our simplified dispersion model, STM. That's the whole idea. But to do the comparison to see how the things work, we actually have done the experiment with this one. So if you look into that, in this slide, we have 4 of them actually. Carbon monoxide, you have seen the summertime how it works, and the wintertime, 2 different time period how it works. And then we have done it for NOx, the concentration pattern around that for summer and winter. Dr. Kumar, the next slide. Yeah, so this is again, if you look into that, this is the same location, but here this is a particular matter, 10 microgram and 10 micrometers, and particular matters 2.5. Similar comparison that we have done. Yeah. Next one, please. So this is actually, this is the model, the simplified dispersion model that we use for the Montgomery County. So these are the values that you can compare with the one that we have shown in the previous 2 slides. And these values are actually used on a simplified model. So, but this takes a very little time to calculate it. So we can actually put them together, and we will actually do our calculation with that. So this again, here you saw the summer and the winter on that time, 2 different part of it. Yeah, please. Dr. Kumar, the next one. Yeah, so this is actually the similar way we did that for the Cincinnati, the 8th worst bottleneck location for the same thing that we have done. This is for the carbon monoxide And then the next is for the NOx, 2 different periods, summer and winter. We just wanted to see how it works. And the next slide, please. And then this is a particular matter for the same thing. We have done it. Please go to the next. Right. So now, since we have done that one, so this is the idea. So now we know how to do it, and we actually found that for 2 locations we did it. So what we are trying to do it is that now in the future we wanted to this expand to for different purposes, and these are the things we try to do. We want to explore how to incorporate that into V2V, V2I, and V2P situation, and then we wanted to do this one actually incorporating that into the CAV model, CAV vehicles, CAVs. We are going to do it. Please go to the next one. So at this point, Dr. Kumar, can you, yes. So the next one, what we do it is that at this point, what we are doing it, so we have these 2 models, and we actually demonstrated how it works, and it has been done. Now we are actually in discussion with an app developer to incorporate all these things in their development and just coming up with the thing. So the next year kind of thing, when we are going to look how we are going to do it, is that now we have that idea, we have demonstrated it works. Now we have to incorporate that into the app. That's what in the summer, that's the most of the thing we will do. But at the same time, what we want to do it is actually now we have kind of shown it 4 locations actually, but we try to expand that to the Ohio different locations to see how it works. So that is the main thing we have to do. But what we try to see during that work is that in our work is, so the moves, the earlier version to 2014, actually, when you compare that to moves 3, it is a really, I think there's a big update. So we wanted to see if we can utilize that information and if we can make the estimates better. That's what we try to do. So our strengths, and we have tried to work on that. Please, next one. So this is actually, we wanted to thank actually, of course, to our current University Transportation Center with University of Michigan. And before that, some of these work actually getting back to Ohio, University of Akron with them, OTC, or Transportation Centers, that I worked in 2009, that time. And then we worked with Purdue and University of Michigan system. Now we are with this one. So I have to thank all of them, because all of we build up all our work from there. And then, of course, our students who are working with this, undergraduate students who are working. Thank you very much. So that's it. So, yeah. So if there's any questions.
Okay. So if you have any questions, please type them in the chat box or in the Q&A. But to get us started, I'm going to ask the question on what do you think is the biggest impact of your research?
The biggest impact is, I mean, if you look into that, President Biden's at the March 31st speech, when it comes to infrastructure development out of $2 trillion proposed amount, around 600 trillions is coming for the transportation. It's, I mean, the big chunk. And then if you look at the CNN news, it says, yeah, all these things, transportation, he said, and then it comes very specifically said to reduce the greenhouse gas emissions and all the things related to that. So one way to reduce the greenhouse gas emissions and everything is that, first thing is that if the congestion is the big thing, when you have it, the emissions are going to be really high and you are going to link it in there. So connected vehicles and everything, when you have it, this information fast, so it will make the people who are driving to give some way to move different places rather than going and emitting one place, or even they can reduce their time traveling rather than getting the congestion. So that will reduce the greenhouse gas emission. So that's the big effect. So when you have an app, that is we believe that is going to help the people. Basically, in the long term, is going to reduce it. I mean, it's a starting way. We try to put the app. We have to improve it a lot. But the thing is that is way to go. That's what.
Okay. Is your work easily transferable to other places in the U.S. other than Ohio?
Yes. Yep. Yes, certainly it will do, because if you look in the moons and the data is everywhere, you have it. So the thing is that only thing we have to do it is someone has to be dedicated to sit there and make a kind of flat data for the counties and the thing. And then the simplified method, we use it because the transportation, if you take the traffic data everywhere, you can get it. A little systems from state to state is a little different, but you are going to get that one traffic data. And the weather report, weather data, and other thing, you are able to get it. So yes, it can be transferable anywhere to US. It can be used. I mean, for the fact, it can be done for anywhere in the world, but mostly we are looking with the moves we started. We are looking in the US. Yes, it is. But at this point, with our capacity starting, we are restricted to this Ohio. But otherwise, yes. Yeah.
How much does adding the seasonal effects on AADT improve your model?
So this is the thing what we do. So we try to use the real-time data for our use. So the thing is that when we use, the only time the seasonal effect is going to jump a lot is if we do not have the real-time data for some reason. Let's say that particular system didn't work on that day or that moment. So that time only we are going to use that ADT data. So that actually gives an idea. ADT, we have it, seasonal effect, if you multiply the factors that we get from the moves and the transportation area, that is actually, it's a substitute more than actually the direct way to do it. Because we really depend on the real-time data. But the seasonal effect, if we do not have the real-time data, then we will go into multiply. Yes.
What's the process for equipping this technology?
I didn't get that fully.
What's the process for equipping this technology?
The word I didn't get it. Probably my
Let me ask it a different way. I'm just not being clear, I don't think. So when you talked about incorporating this with CAV warnings,
right? Yeah.
What kind of warnings were you envisioning?
No, yeah, that's okay. That's it. Because sorry, the thing is, I tried to read, as I said, told you, I left my actual glasses. My apologies. So the thing is that what we try to do it is that the warning is that, see, we are predicting like what's ahead, like half an hour or 1 hour ahead, the path that you are trying. So if we know with estimation at that point, actually the near road concentration of those gases are really high, then you don't want to go there and add more to that place. At the same time, you don't want to get stuck even. So if you are adding that to a GIS technology, GPS and GIS technology, you will find the alternative way. That is, alternative route. So you can move to that way. So you will find another way to go that will actually reduce the contribution of this emission to that location if you are passing. But at the same time, it will safeguard you from getting into that. That is the main goal at the end.